In this lecture, we are going to look at algorithms for computing the Morse-Smale complex. We will begin with understanding of piecewise linear functions. Understandably, this is a first step because in order to design an algorithm, we need the function to be made available to us, and this is often available as a sample. Next, we will talk about the computation of the Morse-Smale complex by first looking at an arc tracing algorithm, which follows directly from the definition, and then we will see a sweep algorithm. Both algorithms are restricted to two-dimensional functions. There are other algorithms proposed in the literature. I will briefly indicate the flood-fill algorithm, which works in 2D and 3D. There are several other algorithms which we will not be able to cover in this series of lectures. Finally, we will talk about how to simplify the Morse-Smale complex by executing a sequence of critical point pair cancellations. To remind ourselves, the Morse complex is a cell complex which represents a partition of a Morse function, the domain of a Morse function, into different cells of different dimensions. So the descending manifolds together constitute the Morse complex with respect to the maxima, where the two-dimensional cells are the hills and the one-dimensional cells are the ridges, and so on. Similarly, the ascending manifolds are together constitute a Morse complex corresponding to the minima. We saw that the Morse-Smale complex was obtained by overlaying the Morse complex, the descending manifolds and the ascending manifolds, in order to give us a partition where each cell is now defined by a collection of integral lines that share a common origin and a common destination. So in order for this Morse-Smale complex to be well defined, we wanted all the intersections between the ascending and descending manifolds to be transversal, in the sense that if an ascending manifold intersects a descending manifold, then it actually crosses the manifold. In this context, we talked about Morse-Smale functions which satisfied this transversal property. The cells of the Morse-Smale complex included a collection of nodes, which were the critical points, the arcs, which were one-dimensional, and connected critical points whose indices differ by 1, and we had quads, which were the two-dimensional cells. Moving over to real-world data, scientific data, when we talked about Morse functions, we saw how the ideas of Morse functions extend to sampled functions, which were represented using linear interpolants. So if I have a piecewise linear function defined over a simplicial complex, one notion that we need to talk about is how is the extension of gradients. So if you look at a point that lies in the interior of a triangle, we know that the function is linear within the triangle. So hence the gradient at any point in the interior of the triangle will be equal, and as shown here on the figure on the left. For points on the edges, the gradient is no longer defined. because the function is not differentiable at this particular point. So if you consider the point as belonging to the triangle on the left, then the gradient is well defined. Again, if you consider the point as belonging to the triangle on the right, then again the gradient is well defined. Whereas for the point that actually is incident on both triangles, the gradient is not well defined. So if we have to define a gradient direction, then it has to be within this range of within this these range of directions. However, we can talk about this is essentially the locally steep direction. So you can imagine what happens at a vertex. There is depending on how we consider this vertex at the center, which triangle it belongs to, there are different directions corresponding to the gradient. Now, one way to define an equivalent to gradient is by considering all these directions and all these vectors and picking the steepest among them, while restricting for example, if you compute the gradient restricted to each triangle, you get one vector per triangle, and we can choose the steepest among each of those vectors. Further, as we will see in the algorithms, we could look at the steepest direction while restricting the gradient to lie along edges. So if we have to define, for example, the locally steep direction at a particular vertex V, and if this steepest direction has to be restricted to edges, then one could compute the directional gradient along each edge and then pick the steepest that is going up. So this is what we mean by locally steep direction, and this is how we extend the notion of gradients to vertices. We will need this notion of locally steep direction when we compute the Morse complex and the Morse-Smale complex. We know that in the smooth case, gradient lines do not intersect. However, in the case of piecewise linear functions, this is not true anymore. As we can already see an example on the top here, right? So this is where the gradient seems to diverge at this point. However, you can imagine a situation where the gradient lines converge as shown in the figure on the left. Similarly, the gradient lines can split as shown in the third figure here. A way to handle these merging and forking behaviors is to simulate this notion of differentiability by allowing the gradient lines to merge, but ensuring that once they merge, the gradient lines stay together. So in essence, what we are simulating is an infinitesimal gap between the different gradient lines as shown here in the second figure, so that the relative ordering between the gradient lines is maintained. So you don't have essentially any intersection or crossing over of these gradient lines. In practice, this essentially means that when two gradient lines merge, then we let them we force them to stay together until they terminate at a critical point. So with that introduction to piecewise linear functions and how the notion of gradient and gradient lines extend, let's talk about the Morse complex computation. In order to compute the Morse complex, we first need to identify the different critical points. We have already seen this in the previous lectures. So given a piecewise linear function, we can classify the critical points by studying the lower link and computing its Betti numbers. This is the first step. The next step, we just follow the definition, and by that what I mean is we begin with each saddle, which I will use in the figures. I will use this glyph to indicate a saddle in order to represent that there is one direction in which the function goes down and one in which the function goes up within the neighborhood of a saddle. We begin two descending arcs from each saddle, from each unprocessed saddle. So these descending arcs look like that. There are two that you begin, and you trace these arcs until you identify the terminating or the destination minimum, right? And the way we trace these arcs is by following the steepest edge within each lower star component. So in order to begin with, the saddle has a link and corresponding star. So remember, we are talking only about two-dimensional functions. So this is a saddle and its link. So I'm not going to draw the star to avoid clutter. I'm going to draw only a few edges, and I'm going to show the lower link. So here is the lower link in blue. And what we are going to do is to follow the steepest edge. We're going to follow the steepest edge within each lower star, right, in order to give us our first edge. And then we extend these arcs until they hit the minimum. Now, how do we do the extension? So let's consider an endpoint of the arc that we are extending, and let's call that V. Now, if V is a minimum, then we are done, right? So if this endpoint here happens to be a minimum, then we are done. We stop there, right? And we know how to recognize our minima. We have already done that in the first step. So if you have reached a minima, we are done. If V is a regular point, is some regular point, then what does the neighborhood look like? So V is a regular point, so we know that its neighborhood looks something like that, where we have one component of the lower link. So the way we extend the descending arc past V is by adding an edge towards its lower link. So by inserting the edge in the lower star, that is the edge of steepest descent, right? And by extending, by adding this edge of steepest descent in the lower star, we have extended the descending arc. Now there is one other condition we need to consider. So in case when we reach V, right, we identify that there is already another incoming arc that has reached V, right? Then we know that there is another gradient line that from a different saddle that has reached V, and we know that when we extend that descending arc, we would have gone past V. So we terminate the current descending arc computation, right? So in that case, we stop the extension. Else, we perform the operation that I talked about. So naturally, if you extend this computation, you will end at a minimum. You will end at a minimum. Hence, you would have computed all the descending arcs in the Morse complex. And eventually we will see how we can find the two cells. That's actually quite simple. Once we have the descending arcs, we have the boundary of all these two-dimensional cells. So this is the simple arc tracing algorithm. So next, we will see how we can essentially compute all the descending arcs simultaneously. So this algorithm requires just a single sweep over the entire domain, after which we would have already constructed the Morse complex. So the algorithm works by sorting the vertices based on decreasing function value and processing the vertices top to bottom. By top to bottom, I mean in terms of function value. So when we are after sorting, when we are processing the vertices, here is what we do. So let's say the current vertex is V. We know again what the neighborhood of V looks like. There is a lower link component and there is an upper link component, right? And this is V, the vertex. The way this algorithm works is that it processes the vertices in decreasing function value, and the processing depends on the type of critical point. And once we are done processing all the vertices, we would have constructed the Morse complex. So if V is regular, so just like what we saw earlier, right? If it already has one incoming arc, right, as in some descending manifold has already terminated at V, in that case you extend that arc by adding the steepest descent into the lower star, right? Now of course when you are processing V, it's possible that you have two arcs terminating at V. That's quite possible because of the merging because of possible merges that could happen. Never mind, you could still apply this rule and add the steepest edge towards the in the lower star, right? Now if V is a minimum, then you know that you are done essentially, right? Because if V is a minimum, then the link looks like that, and you know that some arc has come here and you stop, you terminate, right? So essentially, which means do nothing. If V is a saddle, then you have two lower link components, and hence you have to so you have two lower link components. So note, by the way, that I am drawing these neighborhoods using smooth curves, but the algorithm actually works for simplicial complexes. I'm making these illustrations just for simplicity of or for ease of drawing. So when you have a saddle, and that's how the neighborhood looks like. It may not be a circle geometrically, and also I don't have space, so I make it an ellipse. So in this case, you have you start two arcs in the lower star, right? And if V is a maximum, then you do nothing, because the descending arcs do not touch the maximum at all, right? So that's it. So I just want to point out that when you are a regular point, you need to process V only if there is an incoming arc. It is quite possible that the regular vertex does not lie in any descending arc. For example, it could lie in the interior of one of the descending two-dimensional cells. So for example, the interior of a mountain. That need not be processed at all, right? Right. So this is the sweep algorithm, essentially the same as the tracing algorithm, but easier to process and faster in practice, because it's essentially one operation applied to the vertices in order. So note that you don't need to do any pre-processing to classify the critical points. When you reach the vertex, you can already classify it and then process the vertex. So now, how do we construct the Morse-Smale complex? So far we have constructed only the Morse complex, and specifically I have talked only about descending arcs, but the same algorithm essentially applies to ascending arcs, as you would have realized. So how do we construct the Morse-Smale complex? Well, we can start by computing the descending arcs using the sweep algorithm, for example. And in doing that, we could handle the so-called multi-saddles or monkey saddles. Monkey saddles, when you have which are three-fold saddles, but two-fold saddles really, and in general multi-saddles. And the way to handle multi-saddles is you essentially just start or create k+1 descending arcs originating at each k-fold saddle, and with that minor change, you can handle multi-saddles in the algorithm, and all other steps of the algorithm are essentially the same. You follow the steepest edge within the lower star to compute all the descending arcs. The ascending arcs, if you are to compute them in the second step, we need to be careful. We need to ensure that the ascending arcs do not intersect the descending arcs unless it is a transversal intersection at the critical points. So that's what we will talk about now, and with that we would essentially have computed the Morse-Smale complex. So how do you compute the ascending arcs? Well, you could start by processing all the k-fold saddles and start k+1 arcs from each of these saddles in towards the upper star, right? So now remember, these are ascending arcs, so you go up, right? So that's how you start all these ascending arcs. Now, how do you extend an ascending arc? So this is where we need to be a bit careful, right? So let's look at one example. So here is a vertex V, right? And let's say this is a regular vertex as before, right? Now, what we were saying is that we would like so there is a upward arc that is touching V, and we are extending it, right? So now we have to be a bit careful in the sense that we don't want to cross a descending arc. Now, if so according to the algorithm, we need to find the steepest ascent edge going towards the upper link, right? Now, if this steepest edge in the upper star touches a descending arc, right, then we need to do something different. If it doesn't touch any ascending arc, so for example, if this is the steepest ascending edge, if it doesn't touch any descending arc, then we are fine. However, if it touches a descending arc, then we need to do something different. And what do? We split the triangle that contains this edge and follow the new edge in the direction of the gradient, right? So let's take this triangle that contains V as an example. So here is V, and here is a triangle. Let's give names U and W. Let's say that the steepest ascent was along VU. However, let's say that this contained, however, if VU was already a part of a descending arc, then we don't want the ascending arc to pass through this. So what we do is we split the triangle UVW by adding by splitting it so that you can follow the steepest edge within this triangle. And let me just draw directly that steepest ascent arc, right? And it essentially means that you are splitting, so you are creating new vertices as you go. So what this does is that it does not cause any unnecessary intersections between the descending arc that's going through UV and the ascending arc that is going up from V, right? And then we follow this and take it up, right? So of course this causes some difficulties because you have split a triangle, which means you have created new vertices, and later when you are tracing the ascending arc of another saddle, then you need to handle these additional vertices as well, right? So this algorithm where you do the split is described by Bremer et al. That's one of the references that I have uploaded. The Idesbrunner et al. Paper restricts the ascending and descending arcs to edges of the simplicial complex. So that's the algorithm that we have seen, that we saw earlier. So what that algorithm would do is essentially follow the same edge VU while ensuring that there is no intersection. So it will maintain the sidedness of the ascending arc. Right. So with this, we have computed all the descending and the ascending arcs. So in essence, we have the combinatorial structure of the Morse-Smale complex. So we have already computed all the nodes and the arcs of the Morse-Smale complex. As a final step, if required, we can compute the two-dimensional cells as well. So essentially compute all the quads. And the way we do this is as follows. Here we have a vertex V, and so V is, for example, a saddle. So V lies on a quad. Let's draw that quad. So V and V prime are two saddles, and it is attached to a minimum and a maximum, little m and capital M, right? So this is what I've drawn here is a quad in the Morse-Smale complex. We have already computed all these arcs. So now we need to find the different quads. The way we do this is to first choose some triangle that contains V, right, as the seed, and apply a so-called flood-fill algorithm. The flood-fill algorithm essentially begins from this triangle and expands to its neighbors in a breadth-first search order, right? So this triangle has three neighbors. So you traverse to the three neighbors, and then from there to the neighbors, and so on. The only restriction is that when this traversal should not cross any ascending or descending arc. So you essentially are bounded by the arcs V small m V prime capital M, and capital M V. So via this flood-fill approach with restrictions, you can compute the quad, one of the quads that contain V. So similarly, you can compute all the quads that contain V, and extending this to all the saddles, we can compute the two-dimensional cells of the Morse-Smale complex. So with that, we are done with the description of algorithms for computing the two-dimensional Morse-Smale complex. This flood-fill approach that we saw here extends into an algorithm that can compute the three-dimensional Morse-Smale complex, and to some extent Morse-Smale complex in higher dimensions as well. Some of the authors that proposed the algorithm here have also worked on the three-dimensional algorithm, and if right, so we will stop our description of the algorithm with this slide, and I will let you think a little bit about the running time of these algorithms. That's not too hard to analyze. So I will conclude this lecture by discussing how the Morse-Smale complex represents the function. and what happens if there is noise in the function. So let's consider a one-dimensional example, good for intuition. So here you have on the left a one-dimensional function which has a pair of minimum and a maximum. Well, it has two maxima, and what is shown here is one local minimum. So you can think of this as a hill with a small bump, right? And the bump is actually defined by this minimum maximum pair. If the bump is small enough, then one can imagine that the original function was the big hill and the small bump was essentially noise. So you can imagine a way to transform the function on the left to the function on the right, function on the left f to the function on the right, which is a smoother version of the function, by removing this bump, right? So the cancelling handles theorem formalizes this notion by saying that a Morse function g can always be obtained from f by cancelling two critical points whose indices, Morse indices, differ by 1. This is also a very powerful result from Morse theory, but stated in simpler terms and in the context of the Morse-Smale complex here. Let's look at this result for a two-dimensional Morse-Smale complex. On the top left, you have the Morse-Smale complex that we have seen earlier, with two maxima. Again, the pair UV represents a small bump within the bigger mountain represented by W. In order to obtain a smoother function, as shown on the top right, we cancel the pair UV. So this operation of removing the bump is called critical point pair cancellation. So this cancellation, as you can see, affects the mountain by removing the bump, right? So it's a very natural smoothing operation, but constrained to this particular mountain. When we look at the combinatorial structure of the Morse-Smale complex, this operation becomes very simple, and that's what we will use in further analyses and applications. So let's look at the figures on the bottom. We have the combinatorial structure of the Morse-Smale complex from the top. So essentially this means that we have removed all the geometry, and the glyphs here are the same as before. So you have the maxima U and W, and you have a saddle which is V, and you are cancelling the critical point pair UV. So the cancellation essentially updates the combinatorial structure by removing all the arcs that are incident on the saddle, right? So it removes all these arcs incident on the saddle, right? Removing the two critical points U and V, and rerouting all the arcs that reach the maximum U into the maximum W. So if you look at one of these arcs that was originally going to U, it is now rerouted to go to W, right? So to repeat, all the arcs that are incident on the saddle were deleted, the two critical points were removed, and the gradient lines that terminated at U are now rerouted to go to W, right? So this is one way to realize this cancellation. But if you look at just the combinatorial structure, the simplification is a very easy operation. This essentially is just removing this arc uv, right, and modifying the neighborhood of uv according to a well-defined rule. So there is a systematic way of going from the Morse-Smale complex corresponding to F to the Morse-Smale complex corresponding to G via a collection of combinatorial operations, right? So you can imagine that you can apply this in sequence in order to get a simplified Morse-Smale complex that corresponds to a smoother function with fewer number of maxima. So this simplification is used for noise removal. It is also used for targeted feature reduction and so on. So we will look at several applications of the Morse-Smale complex, and we will note that many of these applications are possible due to this cancellation operation.